Alrighty, let's keep going on some trig-based problems. This one is kind of fun. Let's go ahead and read it. Consider the ladder whose bottom is sliding away from the base of the vertical wall shown in figure 4.211. Now, we've done the whole thing sliding away from the base. Usually we don't. You can actually ask questions in those scenarios about, okay, how fast is the angle between the ladder and the floor decreasing when, when the ladder is 8 feet away from the wall or something like that. But we haven't done that as yet. This one is sort of a variation on that because it asks, show that the rate at which theta 1 is increasing is the same as the rate at which theta 2 is decreasing. Okay, well, I don't like this schematic. It's annoying, so I'm going to redraw it and sort of relabel things, okay? So I don't want to deal with subscript of theta 1 and theta 2, so I'm going to call this alpha, and I'm going to call this beta. I'm going to call this distance right here x, and this distance right here y. Okay, well, let's deal with alpha first. We know that, let's actually include the 18 in all of this, because the last thing I want to do is get an equation with both x and y in there. So let's say I have sine theta is equal to y over 18, right? Because that's its opposite, y over 18. Okay, well, let's go ahead and differentiate this. We have cosine of alpha, d alpha dt, is equal to 1/18, right, because 1/18 was just the coefficient of y, times dy dt. Okay, well, cosine of alpha actually has a particular form, right? It has a particular ratio that we can get from this schematic, because cosine of alpha is the adjacent over the hypotenuse. So that's x over 18 is equal to d alpha dt is equal to 1/18 times dy dt. And of course I can multiply both sides by 18 and then divide both sides by x, and I'm going to get 1 over x times dy dt. So that is how we would find the rate at which alpha is decreasing, right? Well, let's go ahead and let's do the sine, or the cosine of beta. The reason I'm going to do cosine of beta is so that I can get exactly the same ratio, because that's the adjacent over the hypotenuse with respect to beta, and therefore this becomes negative sine of beta times d beta dt is equal to 1/18 times dy dt. Okay, well, sine beta also has a particular ratio. It's x over 18. Let the negative come along for the ride. And when I substitute in the ratio that sine beta represents, or the ratio that represents sine of beta, we again cross out the 18ths, and we have d beta dt is equal to negative 1 over x dy dt. So the rate at which alpha is changing and the rate at which beta is changing with respect to time are exactly the same, except for one is the negative of the other. And that should make sense to us. That should, basically this analytically confirms what we should already know, right? Because the angles of a triangle have to add up to 180, and this angle down here ain't changing, okay? The rate at which alpha is changing has to be mirrored by the rate at which beta is changing. So as alpha is increasing, beta is decreasing, and vice versa, and they're increasing and decreasing at exactly the same rate, and this proves analytically what we already should have known sort of intuitively, okay? Let's go ahead and take a look at another one. This will deal with the angle of elevation. A tracking camera located 1,200 feet from the point of launching follows a vertically ascending hot air balloon. So the hot air balloon is going up. At the instant that the angle of elevation of the camera is pi over 6 radians, the angle theta is increasing at the rate of 0.1 radians per minute. At what rate is the balloon rising at that instant? Okay. Well, we know that we're not actually given any given information, right? Because the information that we are presented with is at the instant, So both of these measurements follow at the instant, which is another way of saying when. So we are basically being asked the question of what is, and that's h right there, what is dh dt when when theta is equal to pi over 6 and d theta dt is equal to 1/10 radians per minute. Now, why they would give us this in a ratio and that in a decimal, I have no idea. So I'm just going to change it to a fraction so that we can actually, do any simplification that is necessary. Now, the angle of elevation, we have h as its opposite, and we have a constant as its adjacent. So let's go ahead and do tangent of theta is equal to h over 1200. We can go ahead and, if we want to get rid of that ratio, change it into 1200 tangent is equal to h. Now let's go ahead and differentiate, see once we do whether we have everything that we need. D theta dt is equal to dh dt. Now, what happens here is I guess you could figure out h and then find the hypotenuse at that particular condition and this, that, and the other. But remember, pi over 6 is a unit circle value. And really what I'm doing is I'm basically asking what 1 over cosine of pi over 6 squared is, right? And that, of course, is radians per minute, and that is dh dt. Now, this, of course, is feet right here, so that is going to give us the units, the feet per minute, because the radians, as always, is going to sort of disappear. Now, cosine of pi over 6 is root 3 over 2. When I flip that over, it's 2 over root 3. Squared is going to be 4/3. So this is going to be 1200 times 4/3 times 1/10 feet per minute. And now all I have to do is just simplify. The 3, of course, can cancel with the 3 inside of the 1200, leaving us 400. The 2 inside of the 10 can cancel with a 2 inside of the 4. And what I'm left with is, again, of course, the 5 can cancel inside of here. Now there's 25s and 100, so there have to be 85s and 400. And that is 160 feet per minute is equal to dh dt. And all it took was simply, basically, like always, deciding from the question stem, do we have given information? If so, what is it? What is our question, i.e., what are we being asked to find? Do we have conditional information? If so, what is it? Now, what is the equation, the model that is going to best make use of the information that I'm both given and being asked for, and represents the physical scenario, the geometry of the physical scenario that I'm presented with. And in this case, like I said, the best choice was tangent. And that was pretty evident by the fact that we're discussing h and we're given this adjacent right here. And the thing is that could you be asked, how fast is the distance between the camera and the thing increasing? Yes, but that's not trig. That winds up going back to a Pythagorean theorem type of question. Okay. Alrighty. Let's do another one. Now, what we have here is a pretty fun one. It's the flight of a falcon. A peregrine falcon flies up from its trainer at an angle of 60 degrees until it has flown 200 feet. Then it levels off and continues to fly away. If the constant speed of the bird is 88 feet per second, how fast is the falcon moving away from the falconer after it is 8 seconds in flight? Okay. Now, what we need to do here is we need to remember, this is going to be a fun one, we need to remember that if we are interested in this distance right here, we are not dealing with a right triangle, are we? No. What is this angle right here? Well, if this is 60, then this is 60 as well, and that makes this 120 degrees. Now, this is 200 feet. We know that. So, constant is the 200 feet and the 120. The things that are not constant, the things that will continue to change as the bird flies, is this distance right here and this distance right here. Well, that looks a whole lot like the law of cosines, doesn't it? Now, this will serve for our A, this will be our B, this distance will be our C, and of course that means that angle C is that 120 degrees. Now, what we basically need to figure out is what is B, right? Because it tells us after 6 seconds in flight. Okay, so our given, right, our given is the fact that the falcon is flying at 88 feet per second. So dB dt is a positive 88 feet per second because it's continuing to fly, right? Now, we need to do the question next. The question, okay, is how fast is the falcon moving away from the falconer? And that's basically what is dc dt. And the condition, all right, the conditional is after 6 seconds. Okay, after 6 seconds doesn't sound like it's actually giving us much, but after 6 seconds accords with a particular b value. Just remember that distance being equal to rate times time, your distance is equal to 88 feet per second times 6 seconds. Okay. Well, 88 feet per second times 6, and I don't feel like doing this in my head, so give me a second. I'll consult a calculator. That just sounds like a headache. I mean, it winds up being 48 times 11, so I guess that would be pretty easy to do in your head if you basically reallocate those factors. But 88 times 6 is going to be 528 feet. Well, if A is 200, then that means that B must be 328 feet, right? Because part of those 6 seconds was in that initial 200 feet, and then the rest, of course, is basically charting out a distance of B. Alrighty, let's go ahead and talk about the law of cosines. So we know that the law of cosines, when we're dealing with C, is going to be cosine of C it's C squared is equal to A squared plus B squared minus 2AB cosine of C. Well, A is a constant. Cosine C is a constant. Okay, so let's go ahead and give me a second. Sorry, that shadow was annoying me. Let's go ahead and plug those in. So C squared is equal to 200 feet squared plus B squared minus 2 times 200 feet times B times cosine of 120 degrees. Now, cosine of 120 degrees is actually negative 1/2. So let's go ahead and simplify this a little bit. Since that's negative 1/2, that negative is going to cancel with this negative. That 2 is going to cancel with that 1/2. And what I'm left with here is 40,000 plus b squared plus 200b. Okay, well, now I simply just have a relationship between b squared and between b and c, and now I can go ahead and figure it out for 2c times dc dt is equal, the derivative of that 40,000 is going to be 0. 2b plus 200, and those both have a db dt, so I'm just going to factor it out. Now, we can go ahead and get rid of the common factor of 2. And what I'm left with, if I'm going for dc dt, is I'm basically left with b plus 100 times db dt, all of that over c. Well, I have b, and I have db dt. I don't have c. So I need to go ahead and use the law of cosines to find that last piece of conditional, of implied conditional information, basically, okay? And so what I need to do from here is, and I may actually pull out a separate sheet of paper to do this simply because I don't want to crowd out the rest of what's going on here. We know that it's going to be c squared is equal to a squared plus b squared minus 2ab cosine c. Now at that moment, I'm looking for c squared, and at that moment, after 6 seconds, I know a is always going to be the same, but at that moment, b has a value as well, 328 feet squared minus 2 times 200 feet times 328 feet times cosine of 120 degrees. Now, let me go ahead and I'm going to get my calculator out here. Let me find it real quick. Okay, so let's go ahead and pull this other page out of the way. And we have 200 squared plus 328 squared minus 2 times 200 times 328 times cosine of, well, let's just go ahead and basically it's negative 0.5, right? We've already identified that. And then we'll just take the square root of that answer, and we're left with C is approximately 461.719. But what I want to do, remember, since I don't want to approximate in the midst of a problem, I'm going to go ahead and store that in for C. Alrighty. So let's go back to our original. We just found out that C as part of our conditional information, part of the implied conditional, is 461.719 feet. And now I have everything that I need to plug into here. I have 428 feet times dB dt being 88 feet per second. And then I'm going to divide that by 461.719, being careful to use the exact value from my calculator. These feet and these feet cancel, okay? And what I'm going to be left with is, let's go ahead and do the fraction. We have 428 times 88 divided by, and actually, since it's just right up there, I don't have to put C, I can just use the answer. And I have 81.574 feet per second. Okay? Now, that, of course, anything with law of cosines, it's just a lot of analytic work, but there's nothing, it's burdensome, it's not difficult. Like, there's nothing in that problem that you don't already know how to do. It's a matter of sort of assembling all the pieces together and doing them all at once in one problem. Alrighty, let's call this one quits. We'll have one more problem on trig-based related rates, and then that will be that. And then we'll convene next week, and we'll start doing sort of mixed review and pulling in the rest of the problems that don't actually fit within any of these subgenres that I've identified. And then we'll move on to the next section and test pretty quickly thereafter. So, again, as always, if you have any questions, please do shoot me an email. Bye.